Cool. Well, I'm excited to share with you guys some work that is both, some of it's recent, some of it's been ongoing for a long time. It's come out of a lot of conversations, most directly with my colleagues that I list here, but really with a lot of the community that's present. And so I'll just share some of what we've been up to thinking about the thermodynamics of computation. And the main idea is pretty simple. It's just how much can this thing compute before its battery dies? I want to know specifically for the technology we have today, but also more generally, what are the fundamental bounds? And like it or not, it's something that we all have to deal with, right? It's something that matters to us every day. So let's look into it. What are the thermodynamic limits of computation? Well, if you ask, the average person on the street, they might say something about Landauer's bound, which is, of course, a favorite test bed for all of us. Everyone's set me up very well, so I don't have to say too much. Basically, to compress state space, you have to pay with entropy flow. Usually you think that's heat. So logical irreversibility implies some heat. Okay, so is that it? Well, from our modern perspective, as people have mentioned, Landauer's bound is basically a restatement of the second law. And so because of that, any quantification of entropy production, it being beyond zero, is going to give us a stricter lower bound on energy consumption. So that'll be more useful for understanding the energetic costs. So that's what our community does, right? I mean, we quantify entropy production. There's this long list. This is not inclusive of, speed, modularity, time semester protocols. All this stuff has costs, and a lot of these communities contribute to that. I've worked on some of it, and the reference here has a non-exhaustive list of some of those things, where we refer to the stack of different costs. So, okay, so we know what to avoid, but do we have a guiding principle for what to do? There was an idea, of course, a long time ago by Bennett and followers that, well, logical reversibility is the thing to do. But again, more modern perspective on that is that logical reversibility is neither necessary nor sufficient for thermodynamic efficiency. So it's really not a guiding principle. So that was really my motivation for this more recent work. And so I'll suggest that a useful guiding principle for energetically efficient computing, and this is really computing in a very general sense. It could be the way your computer is, it could be biochemical computing, a pretty general framework. You would have to satisfy this condition where your physics matches your computation in this particular way to be energetically efficient. So basically on the right-hand side here, of course, I haven't introduced all the notation, but this basically, nu is going to be the distribution over memory states M here, and from time 0 to tau. So basically, we're saying everything on the right-hand side is just something about the computation, regardless of how it was implemented. And it's something about like retrodiction, like which memory state you came from, just given transition probabilities among memory states. And then that needs to match the physics. And so the physics is a little hard to unpack, but this is where all the exciting stuff is. So if you want to be efficient, your physics has to be such that the logical reversal is the same as the physical undoing. So all the daggers here are time reversal operators. And we're time reversing things like momentum, and we're also time reversing things like the memory state, which is going to tell us stuff about, say, magnetism versus positional memories. And this suggests at least two paradigms for energetically efficient computing. We've had lots of great discussions here this week about, what momentum can do with breaking TURs. Salambo was just talking about how underdamped momentum degrees of freedom might affect Landauer's bound. So looking at momentum is something that's enabled by these relations. And if you don't meet these relations, then we have some results, which I'll have to unpack this thing, but it's basically saying that you're going to have as much entropy production as basically this this undue mismatch between your actual distribution over memory states and what you would get by trying to undo the computation if you were doing the physical undo. I think I'll just kind of blast past a lot of this, but basically memory states can be thought of as coarse grainings of physical states. There's usually a separation of timescales so that our memory is usefully accessible. It's a typical thing. You can change the Hamiltonian of the system and the interaction to create some, just in general, a probabilistic transformation among memory states. But we actually want our computers to do the right thing. So there's a useful limit you can take, and we learn a lot by basically taking this nearly deterministic limit. And in that case, we can approximate a function C, which is just a deterministic function on the memory states. Here's just a few very simple examples. And the results that we have are basically in terms of any function C, which is just any mapping of memory states. And we learn thermodynamic consequences of different functions. I'll mention metastability here and there. And that is basically just saying, okay, you can have some steady state distribution over your memory, pi. It doesn't need to be equilibrium, it could be. You can have, the notation here is, the superscript is saying that you are restricted and renormalized to this space, like to the left state. And then a metastable state is just like any combination of local steady states, right? And that really simplifies the thermodynamics. And it is basically how most computers work. So we can kind of get away with surprisingly easy analysis for some things. So okay, here's just an example of underdamped Langevin dynamics implementing erasure. And at the beginning and end, it's basically metastable. And in the beginning, it can do whatever the heck it wants. At the end, it's going to have some basically channel of what it does, which is independent of the implementation. There's going to be some transition probabilities. The framework we use is very general. We can talk about temperatures, chemical potentials, and all that. And it's the standard one we've heard all week, so I won't elaborate too much. The second law indeed implies Landauer's bound. So can we place stronger bounds on sigma? In particular, can memory transitions place strong bounds on sigma? And that's what we found in the reference here, that the entropy production is indeed at least as large as this relative entropy between these joint probabilities between initial and final memory states. And so we can unpack this. So basically, this is implicit then in this relative entropy to say that for the relative entropy to be 0, you must have the physics matching the computation, as I suggested earlier. And so this talks about momentum when you're taking the time reversal of the distribution. It also talks about, as I hinted at, it talks about the advantages and disadvantages of, say, positional storage that we usually study, and spin storage, which is, say, magnets that are common in computers. Alec read a paper on that we have that I suggest looking at. And let me just cover this part on near determinism. So here's just some computation. And here's some recent results that we have that each of these, we call them contracting memory classes, which is basically all the stuff that maps to the same thing according to the deterministic computation. That's a contracting memory class. And each of those contributes individually to the dissipation. So you can just look at each one individually and you say, what is the undue mismatch of the actual initial distribution versus if you had put the distribution forward and then tried to physically undo it. But there's really no guarantee that you're going to come back to your initial distribution. So how can we try to make this happen? So one way is to design basically like an attractor landscape. And so here's kind of an idea of solid lines are kind of attractive, dashed lines are repulsive. So we have kind of this bifurcation structure idea. And then you can see, well, if you trace it back in time, you would follow basically the attractors again. And so then you can start to see, well, if I have an attractor, if I go forward like this pitch bifurcation, if I went back on it, I would match well. Okay, so that's good. On the other hand, if I had a time symmetric implementation of erasure, then it's necessarily going to be something like a cusp catastrophe. And so because of that, you're losing stability, you're dissipating a lot. We have an error dissipation trade-off for time symmetric protocols. And basically—
We're over time, so could you summarize and conclude?
Great.
Thanks.
For sure. Yeah, let me just summarize to say that that bifurcation picture is a little oversimplified, but if we think about attractors in the more general sense, then we have this persistent metastability going from metastable to globally stable to metastable again. That's a way to achieve it. And finally, I'll just note that our relations allow us to talk about how momentum and time asymmetric degrees of freedom can help us. So with that, I will happily take questions.
Thank you very much.